Hello, Algebra 2, and welcome to Chapter 10, Sample Spaces and Probability. So, in this section, we're going to look at what is probability and what is a sample space. And I know we know the term, but in general, probability is going to be the likelihood of an event happening, the likelihood of an event occurring. And it will involve, I think occurring has two R's, it involves looking at a ratio of favorable over total outcomes to get that probability. So if an event is absolutely certain to happen, which is a really hard probability to find, we say the probability of that event, and this is how we write it, equals 1, which is equivalent to 100%. If an event is absolutely certain to not happen, then the probability of that event equals 0. So you can try and think of something that's absolutely certain or absolutely certain not to happen. Those are the extremes. Everything else is going to lie somewhere in between, which is why it turns into a decimal, a ratio, or a percent. So let's say something was evenly likely to happen as well as not happen. We would say the probability of that event is, we could say 50%. We could say it's a probability of 1/2 or a probability of 0.5. That's when you have an even chance of it happening or not happening. So the impossible side is 0, the certain side is going to be 1. Okay, so then we have some terminology that we want to go over. An outcome is when you have the possible result of an experiment. So the outcome of an experiment might be heads is a possible outcome when you toss a coin, or when you roll a die. You might get a 6, you might get a 5. All of those are possible outcomes. The sample space is when you look at all of the possible outcomes. So when I toss a coin, I could get a heads or a tails. If I were to toss 2 coins, your sample space actually increases because I could get a heads and then a head. I could get a head and then a tail. I could get a tail first and then a head. Or I could get a tails and then another tails. So notice you have a lot more possibilities when you toss 2 coins. And so then we can look at the event. The event is the set of those outcomes. So for instance, if I want to look at what's the probability of, say, rolling a 6, that would be the rolling a 6 is the event I'm looking at, and it would be a subset of the total sample space of just rolling the coin. So that's kind of just to get back into terminology. Counting sample spaces. So we want to figure out what is the total sample space here. You roll a die, then you toss a coin. How many events are possible in the sample space? So if I roll a die, we know that there are 6 possible outcomes from rolling a die, because you can get a 1, 2, 3, 4, 5, 6. We're assuming it's a normal die. Then I toss a coin. So we know that when I toss the coin, there are 2 possible outcomes. So this is called the counting principle. When you're trying to find the total sample space, the number of events in that sample space, you do the counting principle, which is you multiply the 2 possible outcomes together. So 6 times 2 would be 12. So if I roll a die, then toss a coin, I should have 12 possible outcomes. And we can diagram them, but it becomes kind of a mess. So this is called your counting principle, where you're just then going to multiply the numbers together. So for instance, if I were to go to In-N-Out Burger, and let's say you have a choice of just the 3 shakes, chocolate, vanilla, strawberry, 3 burgers, hamburger, cheeseburger, or double burger, how many different possible meals could result Well, that's going to be the 3 possibilities from the shake, the 3 different types of burgers, and so together the total sample space would be 9. So the total sample space is important because that's always going to be in the denominator of your probability. Okay, now let's look at 2 types of probabilities that we'll be looking at. You have theoretical, which is what you expect to happen. Like when I toss a coin, I could get a heads, I could get a tails. Since there's 2 events, it's a 50-50 probability for one or the other. But when you actually toss the coin, that's the experiment. What did you actually get? Okay, so theoretical probability, to find it, we look at the number of favorable outcomes. That would be, if I wanted to find the probability of getting heads, well, there's only 1 head on a coin, but there are 2 sides, so there's a total of 2 in the sample space. So the probability of tossing a coin and getting heads is 1/2, the favorable over the total number of outcomes, which is based on your sample space. Experimental is what actually happens. So that's going to be the number of successes over the number of trials, and then you just make a ratio out of the 2. So if a coin is tossed 20 times and lands on heads 8 times, that means the theoretical probability is not going to be concerned with the experimental, because theoretically, if I toss a coin 20 times, my sample space is those 20 times that I toss the coin. I would expect to get heads half of those, because the theoretical probability is still 1/2. However, experimental is what actually happened. That's going to be the 8 times out of 20, and then you can go and reduce that, which would be 1/5. So notice it's a very big difference, the experimental. In general, the more trials in your experiment, the closer it should get to the theoretical. So let's then look at this. A student taking a quiz randomly guesses on 4 true-false questions. What is the probability of their getting exactly 2 questions correct? So here is how we could look it out. I means incorrect, C means correct. So to get, as an outcome, to get no problems correct is only one possible way to do that. The number of ways you can get just 1 question correct, so that's here's you could get the first one correct, the second one, the third one, or the 4th one. There are 4 ways that can happen. To get exactly 2 correct, so you could get the last 2, you get the second and the 4th, the middle 2, the first and the last, the first and the third, or the first 2. There are actually 6 different ways for that to happen. And then again, for 3 correct, so the last 3, the first 3, and then combinations thereof, there's 4 ways you can get exactly 3 correct. There's only 1 way to get all 4 correct. So what we have here is, when we add these up, 10, 15, 16, there are 16 different ways that I can get problems correct in this situation. So that's going to be my total sample space. That's the total outcome. What we're looking at is the probability of exactly 2 correct. So that's going to be the 6 out of 16, which will then reduce to 3 out of 8. One of the things we like to do with probability is use the probability of an event, whatever that percent is or that fraction, to make predictions about what has not yet occurred. So for instance, in the US, a survey of 2,184 adults ages 18 and over found that 1,328 of them have at least at least one pet. The types of pets are shown in this histogram. So dogs, cats, fishes, birds. No reptiles there because we haven't a gecko, but that's okay. What is the probability that a pet owner chosen at random will own a dog? So first of all, notice that the subset is a pet owner, not all the adults that were surveyed, but only the pet owners. So the first thing we would have to do is add up all these people that actually have pets. And it turns out that that is the 1328, so that is a subset. So total favorable would be 1328, and we want to know what portion of those own a dog. That will be 916. So that's the probability of a pet owner owns a dog. And then if we reduce that, it doesn't reduce very far, but it would be 229 over 352. That would be our probability of a pet owner owning a dog. So you have to be careful and read the questions because we didn't ask how many adults surveyed own a dog, only the pet owners. So you had sort of a subset of the total. Another thing we can do with probability, and this is what you did last year, is use probability in geometry using your formulas for geometry. So for instance, we have this dartboard here, this yellow and red dartboard. And you throw a dart at the board. The dart is equally likely to hit any point inside the square board. We want to know what is the probability that the dart lands in one of the two yellow sectors in the smaller circle. So in here or in here is the probability we're looking at. So the probability of hitting one of those two yellow sectors is going to be the favorable over the total. So the total in this case is going to be the area of the big square, and then the favorable is going to be the area of the two sectors. So going back to your geometry, we look at the area of this square. Well, if this part is 5, then this is 5. So this has a length of 10. The area of the whole square is going to be 100. To find the area of the circle, it's basically half of a circle with a radius of 2. So remember, the area of a circle is pi r squared. So that's going to be 4 pi. But then we only have half of that, so this is going to be 2 pi. That would be, which we could then reduce to pi over 50. That would be the probability of landing in one of those two little sectors of a circle. Okay, so probability is basically, what are you looking for? What's the possibility of that event over the total possible outcomes? Now, sometimes it's actually easier to find the probability of something not happening, especially when it is a much bigger number than what would happen. So, for instance, if you were to roll a die, we know that the probability of rolling a 4 is 1 out of 6. That means then the probability of not rolling a 4 is 5 out of 6. So it's easier to count what you would do and then figure out from there what didn't happen. How do we express that? We express that this way. So let me kind of emphasize that. The probability of not A, that's what that means. The probability of not A, it equals 1 minus, because remember, together, the total probability has to equal 1 of both events happening and not happening, and you can't go greater than 1. So if it didn't happen, that means that's 1 minus the probability of it happening. So here's what happens if you roll 2 die. You're going to want to be able to utilize this. You could get 1, 1, 1, 2, 2, 2. You could get a 5, then a 4. These are all the possibilities when you roll 2 die. So notice that the total here is 6 times 6. There are 36 possible outcomes. That would be our total sample space. So what is the probability that the sum is not 6? Well, there's a lot of sums if I'm going to go through and sum up all of these. So let's just find the ones that are 6. So we're going to find the probability, the sum is 6, because that will equal 1 minus the probability the sum is not 6. So let's find our 6's. So 5 plus 1 is 6, 4 plus 2 is 6, 3 plus 3, 2 plus 4, 1 plus 5. 1, 2, 3, 4, 5. So it's a lot easier just to count those 5 possibilities. So what is the probability the sum is not 6? Is 1 minus the probability of a 6, sum of 6, which equals 1 minus, what do we have? 1, 2, 3, 4, 5. 5 out of 36. So when we make a common denominator out of our 1, that is going to give us 31 out of 36. That's a lot easier just to count those 5 sums than to go through and count everyone that wasn't there. All right, so that's one of the helpful uses of finding the probability of the complement, is what we call it, probability of not A. So what's the probability that the sum is less than or equal to 9? Well, then let's go ahead and find, so the probability the sum is less than or equal to 9 is the same thing as doing 1 minus the probability the sum is strictly greater than 9. And there's less of those, so let's count those. So 9, strictly greater than 9. So we start with 10. So here's 10, 10, 10. All of these are going to be greater than 10. So we have 3, 4, 5. We have 6 of them. So 1 minus 6 out of 36 is going to give us 30 out of 36. So the probability that the sum is less than or equal to 9 reduces to 5, 6. That's how you would use the complement. All right, I hope that helped, and then don't forget to do your classwork associated with this and the online homework.